Chapter 9 is all about sequences and series. A sequence is simply a list of numbers. Usually there is some pattern to the numbers. So in this case, we've got plus 4, plus 4, plus 4, plus 4. Certainly we could list out the next several numbers, 27, 31, 35, and so on. The question we want to answer is, what is the 794th term of this sequence? So 7, 11, 15, 19, 23. If this pattern continues, which term would be the 794th term? So looking at the sequence, we start with 7, and notice we are adding 4 a bunch of times. We're just adding 4 over and over and over again. To get to the second term, I have added 4 one time. To get to the third term, I have added 4 2 times. To get to the fourth term, I add 4 2 3 times. So to get to the 794th term, I will have added 4, not 794 times, but 793 times. So we want to start at the first term, which is 7. We are adding 4 one fewer times than the number of terms. So in this case, 7 plus 4 times 793. Our 794th term is 3,179. So a sequence, we said before, was a list of numbers. An arithmetic sequence is a sequence where the difference between consecutive terms is constant. Sequence where the difference between consecutive terms is constant. So on this previous example, the difference between 7 and 11 is 4, 11 and 15 is 4, 15 and 19 is 4, and so on. We call that difference the common difference. It is possible for that common difference to be positive, like it was in the previous example, or it could be negative, where the terms are going down by the same value over and over again. The formula to find a specific term in an arithmetic sequence is a sub n. So a is a term from the sequence. If I'm looking for the nth term, a sub n is equal to a sub 1, that would be the first term, plus the quantity n minus 1 times d. So a sub 1 is the first term in the sequence, n is the number of terms, and d is the common difference. Example 1 just wants to know, is each sequence arithmetic? 5, 11, 18, 26, ... Notice our sequence does have a pattern, and that pattern does involve addition. Here it's plus 6, and then plus 7, and then plus 8. So we could come up with the next several terms, add 9, 35, add 10, 45, and so on. It is not arithmetic because we do not have a common difference between consecutive terms. This one, notice my terms are going down. 717 minus 21 gives me 696, minus 21 gives me 675, minus 21 gives me 654. So yes, this is an arithmetic sequence. Our common difference is negative 21. Example 2 asks us to use an explicit formula to find the 225th term of the sequence 5, 11, 17, 23. First, we should verify that we do have an arithmetic sequence, plus 6, plus 6, plus 6. We are looking for the 225th term. That is equal to the first term, 5, plus the common difference. We're adding 6 over and over again, times 1 fewer than the number term that we're looking for. 225 minus 1 gives me 224. And we get the 225th term to be 1,349. The arithmetic mean is the average of any two numbers. Really, it's the average of all the numbers. We're just looking at the average of two numbers. It will find the missing term in an arithmetic sequence. So you have certainly heard of mean, median, and mode. When you hear that phrase mean, it's actually talking about the arithmetic mean. There are other means as well. We'll talk about geometric mean soon enough. But arithmetic mean is average. That's the mean you're used to. Find the missing term from the arithmetic sequence 24 blank 57. 24 blank 57, so we find the average of those numbers, add them together, divide by the number of numbers, 81 over 2, 40 and a half. Notice 24 plus 16.5 gives us 40 and a half, plus 16.5 gives us 57. Section 9.4 is on arithmetic series. A series is the sum of a sequence. So we take the terms and we add them up. So here we're given 33, 37, 41, 45, ... We want to not find the 138th term, but we want to add up the first 138 terms. And to do so, let's take a look at a little different example. We'll come back to that one. Suppose we wanted to add up all the numbers from 1 to 100. So if we want to add all these numbers up, one way we could do that pretty quickly is if we take a look at the first number and the last number and we add those two together, I get 101. Or if I add the second number and the second to last number, I get 101. And the third to last gives me 101. And these two give me 101. And 5 and 96 give me 101. So I'm going to have a bunch of 101s here. Question is, how many 101s am I going to have? Well, I have 100 numbers and I'm pairing them up. So it should be half of the number of numbers I have. There should be 50 101s, and we can multiply that out and get the sum. So to find the sum of an arithmetic sequence, the formula we're going to use, let's go ahead and define these, and then we'll come back to that example. So a series, we actually just define that, the expression for the sum of the terms of a sequence. An arithmetic series just means that I'm adding up an arithmetic sequence. The formula, this 101 came from the sum of the first term and the last term. So our formula, I'm going to add the first term and the last term. And then also notice I have an n over 2 right there. That's the number of terms divided by 2. That's how we get that 50. So the sum of the first n terms is equal to n over 2 times the sum of the first term and the last term. This is only if we have an arithmetic series. So going back to that previous example, 33, 37, 41, 45, ... We want the sum of the first 138 terms. The formula said n over 2, so number of terms divided by 2, times the sum of the first term, 33, and the last term. And the problem is they don't tell us what that 138th term is. So what we're going to do is we are going to find the 138th term using that sequence formula. So the 138th term is equal to the first term plus the common difference, plus 4, plus 4, plus 4, times n minus 1. That will tell us what the 138th term of this sequence is, which is going to tell us what we add 33 to in our sum formula. So I've got 33 plus 4 times 137. The 138th term is 581. So I'm taking 138 over 2 times 33 plus 581. and I get 42,366. Last example, part A asks us to find the sum of 1, 4, 7, 10 for 125 terms. First of all, we can only use these formulas that we've been looking at if I have an arithmetic sequence. You always need to verify that first, plus 3, plus 3, plus 3. If it's not arithmetic, the formulas that we just looked at today do not work. So in this case, I want the sum of the first 125 terms. The sum formula is n over 2 times the sum of the first term and the last term. Again, just like the previous example, we are not given what that last term is, but we can find it using the sequence formula. The 125th term is equal to the first term plus the common difference times one fewer than the number of terms. So the 125th term is 373. So the sum of the first 125 terms is 23,375. Part B, similar problem. We have an arithmetic series here. We're trying to add up the terms of an arithmetic sequence. Notice it, plus 2, plus 2, plus 2. Don't just add up these 8 numbers. There's a whole bunch of numbers in between there. That dot, dot, dot means there's other stuff in there that we don't know. We do have an arithmetic series, so let's use the arithmetic series formula. Sum of an arithmetic series is n over 2 times the sum of the first term and the last term. And the problem is this one, it doesn't tell me how many terms I have. The previous problems told me how many terms I need to add up. This one, I don't know how many are in there, but we can figure out what n is. Again, we're going to go back to the sequence formula. The sequence formula says the last term is equal to the first term plus the common difference, plus 2, plus 2, plus 2, times n minus 1. I can then solve this equation for n and plug n into my sum formula. So subtract 18 from both sides, divide both sides by 2, is that 265, I think. And to add 1 gives me 266 total terms. So I do 266 over 2 times the sum of the first term and the last term. 75,278. The other thing we need to talk about quickly here is summation notation. Summation notation looks like this. It uses this giant Greek letter sigma. And the way summation notation works is whatever this is at the bottom, first of all, it defines the variable. Variable is n. This tells me that the first number I'm plugging in for n is 1. So this is the first number to plug in for n. And then we're going to plug in all the integers starting at that value and ending at the value up at the top. This is the last value to plug in for n. The giant sigma, that tells you to add. This is telling us to take the sum. And this right here is the rule. This is where we're going to plug in for n. So n equals 1. I'm plugging in 1 for n first. That gives me 3 plus 2. Pretty sure that's 5. Now plug in 2, 6 plus 2. Plug in 3, 9 plus 2. Plug in 4, 12 plus 2. Plug in 5, 15 plus 2. I stop there because that's the value up at the top here. This is the last value to plug in for n. The sigma tells me to add those values up. So let's see here. We have 31 and 13, 44, 55. Problem like this will often be no calculator. If it is on the calculator part, we can use our calculator to evaluate summation notation. It's pushing alpha, the green alpha button, and then window. This screen will pop up, and then scroll down to number 2. N equals 1. If you want to use n, you can. It's right here in green. Alpha log will work. Usually on the calculator, it's easiest just to use x, which is right next to your alpha button. X equals 1. You can scroll up to the top and put in your 5. And then remember, we're using x instead of n, so 3x plus 2. Then verify that we do get 55. So example 6 here, we could evaluate this sum. Plug in 2 gives us 1. Plug in 3 gives us 6. Plug in 4, 16 minus 3. Plug in 5, 22, or 25 minus 3. Plug in 6, 36 minus 3. Plug in 7, and add them up. I'm feeling lazy. And we can verify by doing this. X equals 2 to 7 of x squared minus 3. Does indeed give us 121. Sometimes you might run into ones like this. Suppose it's a no calculator problem. And we have the sum as n goes from 1 to 55 of n minus 11. I think pretty clearly we're not going to plug in 55 values for n and add them all up. But let's start by plugging in at least a few values for n. So if I plug in 1, I get negative 10. Plugging in 2 gives me negative 9. 3 is negative 8. 4 is negative 7. 5 is negative 6. I'm adding them up. And hopefully we recognize that we have an arithmetic series. I start with negative 10 and I'm going up by 1 each time. So the sum of an arithmetic series is n over 2 times the sum of the first term and the last term. So if I plug in 1, I have 1 term. If I plug in 1 and 2, I have 2 terms. If I plug in all the values from 1 to 55, I think we can agree we have 55 terms. The last value I would get, remember I'm plugging in all the numbers from 1 to 55, so the last number I plug in is 55, which gives me 44. The last number I would have on my list here is 44. So we can add those together, get 34 times 55 over 2. If it's no calculator, I'd probably do 34 divided by 2 and get 17, and we could do 55 times 17 without a calculator. And 935. Notice on ones like this, we would not be able to do that because we don't have an arithmetic series, plus 5, plus 7, plus 9, plus 11, and so on. So this one's not arithmetic. Don't try to use a formula for this one. But if it is arithmetic, you certainly can. That is it for the notes from sections 9.2 and 9.4. That's on arithmetic sequences and arithmetic series. Reach out if there's anything we have questions about.